Okay. Professor Minh. Professor Minh. Yes, definitely. Yes, see you around.
Okay. 안녕하세요. Great. I actually learned it 19 years ago, and I live in Long Island, New York now, but I'm from Vietnam, and guess what? The first country that I went outside Vietnam was Korea. Korea was, have a special place in my heart. I have such a good time back then. It was 19 years ago, so probably before some of you were born. Okay? So I probably know Korea before you do. Yes, so I'm going to talk about attentive human action recognitions, and now I'm working on developing algorithm for human behavior analysis, and here human behavior could be the action, interaction. Oh, something wrong. Okay, sorry.
Yeah, it's cleared.
Okay, good. Better. Sorry. Yeah. So, okay. So here, human behavior could be the action, interaction, or activity of a person or people in a video. So given a video, I want to recognize their action and interaction automatically. Human behavior could be the facial or head movement, and we might be interested in knowing how happy or how depressed a person is. I'm also interested in attentional behavior. Basically, if I show a person an image or video, I want to predict where the person is going to focus their attention on. Okay? So by analysis, I'm interested, several problems. One is recognition. Recognition means to recognize something that has already happened. Given a video, I want to come back and analyze what's happened in the video. And there's another problem that I'm interested in called prediction. Prediction means you observe something now and you try to predict what's going to occur in the future. Now, however, prediction is usually very difficult because human behavior is so stochastic. What people are going to do in the next second or next 5 seconds is very difficult to predict. So there's a third category that I call early recognition. Basically, it's to recognize the ongoing activity, something that has already started, but it hasn't finished yet, and I want to recognize that activity as soon as possible. And I call it early recognition. Now, so why should we care about human behavior? Well, there are many applications of human behavior analysis. First of all, human behavior analysis can improve security. If you can analyze and recognize people with depression, then we can improve healthcare. Human behavior analysis can be useful for human-robot interaction. Imagine that you want to build a robot that can collaborate with people. Then the robot must be able to recognize the human action and also anticipate what the person is trying to do, so it can have the fluent collaboration with the human, right? And also, being able to predict visual attention of a viewer will allow us to deliver better content, saving network bandwidth. Suppose that we can predict, the viewport, what a person is going to see given a 360-degree video, then we only need to stream the part of the person is going to view in high resolution. So that is the work that started with Professor Ji-Hoon right here, and this is something that we are trying to extend the work and build an application of this work. Okay, so the main problem that I'm working on are recognition, early recognition, prediction of human action, face behavior, and visual attention. I'm also interested in solving some supporting problems, such as human body or hand detection in images and video. Another problem that I'm interested in is crowd counting. Given an image, we want to know where the people are and count how many people in that image. Now, human behavior analysis, depends on the performance of a recognition system. Usually depends on the amount of training data that you need, you use to train that recognition system. And for human behavior, it's very difficult to collect annotated training data. So much of my research has been driven by the fundamental question in machine learning. How do you learn from unlabeled sample? How do you learn from weak and noisy annotated sample? Or how do you learn from complementary sample? If we want to recognize human behavior, recognize and predict human behavior, we need to also to understand how humans behave, learn, and perceive. So much of my research also, I collaborate with people in different departments to answer some interdisciplinary problems in human behavior, perception, and learning. So today I'm going to talk about one specific work on human action recognition, and how to use complementary samples. Actually, I'm going to talk about two parts. In the first part, I'm going to talk about one specific project, and in the second part, I'm going to give you an overview of other research projects. Okay. Okay, so the first part is called attentive action context factorization. So the goal here is we want to recognize human action in video. So the type of action that we consider here are, for example, run, drive, kiss. Okay. Now the problem is human action recognition is very challenging due to the subtlety of human action and also the complexity of video space. So it's usually very difficult to identify and attend to the relevant information. So a common approach for human action recognition would be the following. Now, we collect positive and negative data and train a classifier. For example, consider training a kiss classifier. What we would do is we're going to collect a number of positive examples of a kiss. Okay? And then we also collect negative example of a kiss, which are probably other human actions that are not a kiss. And then we're going to train a classifier, a binary classifier, to separate between the positive and the negative examples. In this case, I show SVM, but you can use your favorite classifier. Now the problem with this approach is in the positive example, not only you have the action content, you also have the contextual elements. What I mean by that is, if you look at the video of a kiss, usually you see, it is filmed in a specific way. Basically, there's a slow-moving camera panning around the two people kissing. So, if you train a classifier to recognize a kiss, what the classifier does is actually focus on learn the motion of the camera instead of the motion of a kiss. So essentially, it will fail to recognize a kiss just because there's so much contextual things that always occur with the action. And by context, I mean there are various types of context here. It could be the background context. For example, a kiss is more likely to occur in the living room. It could be the camera context. A kiss, you see the slow panning camera. It could be the situation context. For example, a kiss is more likely to occur after a dance. Okay. Now, context often co-occur with the action. So the learn classifier focus on the contextual cues instead of the action content. So the learn classifier will not generalize if it will not work if the context is different from what it is trained on. For example, Suppose that you have a classifier to recognize the toothbrushing, and most of the training example are in the bathroom, then it will fail to recognize toothbrushing if it occurs outside the bathroom. Okay, so our goal in this work is to learn classifiers that explicitly separate the action from the context. And one technical challenge that we have is the context always co-occur with the action. So to some extent, it will be very difficult or even impossible to separate between the context and the action if you just want to train a binary classifier to separate between the two sets. At this point, I should emphasize that in a video, there will be several components, what I would call the action component, the context component, and noise. Noise is something that doesn't always co-occur with the action. So if you have a lot of training example and you train a classifier to separate between the positive and negative example, noise will be suppressed. However, if something always co-occur with the action, then even if you have a lot of training example, it might still be very difficult to separate between these two factors. So one approach here is to provide detailed annotation. Suppose that we want to collect an example of a handshake, for example. We could, for detailed annotation, we can provide delineates the component that correspond to the handshake and the one that correspond to the context. However, it is very difficult to obtain detailed annotation. First of all, this is a laborious process. Imagine that you have to do it for every training example and for thousands of action classes, 1,000 of video clips for 1,000 of action classes. This approach is not scalable. But another problem that is actually more problematic is it is very ambiguous. Suppose that we need to annotate the temporal extent of an action. When would you consider that the two people are shaking hands? When the two hands are in contact, or when one person starts extending a hand toward the second person? So if you ask two individuals to annotate this, to delineate the start and the end of a handshake, you're going to get different inconsistent answer annotation. So our idea in this work is very simple. We're going to use something called the conjugate sample of human action. Conjugate sample is something that contextually is similar to the action sample, but it doesn't contain the action. So the differences between an action sample and the context sample and the conjugate sample is the action component. And the similarity between an action sample and the conjugate sample would be the context component. So if we have a conjugate sample and we analyze the differences and the similarity between these two samples, we will figure out the action and the context component. So how do we obtain conjugate sample in the first place? So in this work, we're going to make the following assumption. Suppose that the action is in the middle of the video clip. We're going to look at the video sequence before the action sample or after the action samples. Those are the ones that likely to contain the same set of people, the same background, but they do not contain the action. So the middle part is the action sample. We just look at the one either before or after as a conjugate sample. So to some extent, what we propose here is to use more data for training our classifier. However, note that we don't propose to use, our method doesn't require actual annotation effort. We just propose not to throw away the data. Usually when people collect this type of data for human action recognition, they identify the location of the action and they throw away the part before and after the action samples. Here what we propose is not to throw them away, but the annotation effort is basically the same with the method usually done I describe how to get conjugate sample, one question is how to use conjugate sample effectively. Well, there are several possible approaches here. One approach is to subtract the conjugate sample from the action sample. However, there's no direct pixel-to-pixel correspondence between these two samples, so a direct subtraction between these two samples wouldn't work. Another approach is to use conjugate sample as negative examples. However, this ignores the importance of context for recognition. So in this work, what I want to do is to explicitly separate the action, the context from the action, but I don't want to ignore the importance of context. I still want to use it for recognition. The third approach is to use conjugate sample as positive example, but that corresponds to using having noisy labels, and this will degrade the performance of the classifier. So in this work, what we propose is this is a proposed framework to separate action and the context factor. Remember that we have an action sample and we have a corresponding conjugate sample. What we're going to do is we need to learn an action extractor, a network to extract a feature vector that represents the action component of a video clip. So this is the same network. If I apply it to the action sample A, I'm going to get our feature vector called FA to represent the action component in that video clip. If I apply it to the conjugate sample C, then I get our feature vector FC. So my assumption is the conjugate sample A doesn't contain the action. So what I want is FA and FC to be different. So we can penalize for the similarity between FA and FC. At the same time, we're going to learn a context extractor function G. And if I apply G on the action sample A, then we would get GA, and if we apply to C, we got GC. And the assumption is the action and the conjugate sample are contextually similar to one another, so GA and GC should be similar. So I'm going to penalize for the differences between GA and GC. Now that we can separate the action component FA from the context component GA, at the end, we still want to use both of them for recognition. So I'm going to learn the classifiers that combine both the action and the context component and use it for classification. And we have the classification loss to penalize, to make sure that these two factors are still useful for classification. And finally, it's basically the joint learning framework for the action extractor, a context extractor G, and a classifier H. Okay, so now for prediction in testing, in training we need both the action sample and the conjugate sample, but in testing we only need the action sample. Given the video clip, we're going to put it through the action extractor, the context extractor, and then through the classifier for a classification decision. So our framework enables detailed analysis, and basically if we want to understand the contribution of the action factors, we can switch off the context branch. If we want to understand the contribution of the context factor, we can switch off the action branch. Okay? So this is a summary of our approach. We propose a method that automatically separates between the action from the context. We separately model the action and the context, and then we combine them for action recognition. This approach enables fine-grained analysis, and our method uses conjugate sample of human action, but conjugate samples are easy to collect. Okay, so let me show you some experiment. So the first experiment was done on the action trace dataset. So this dataset contains about 3,000 video clips with 13 action classes. And the backbone networks for feature extraction, we use a C3D network. Basically, it's just a 3D convolution neural network. and the input is a block of 16 RGB frames, and the output is a feature dimension of 4096 dimension. I should also mention that the input to our network is a video clip, not a single individual frames. Okay, here's the experimental results. What I'm showing you here are the average precision. And for average precision, the higher the better. Okay. The rows show you different category action categories, and the columns are different way of using conjugate sample. The default approach, the baseline approach, is not using the conjugate sample at all. That's a normal way of training a classifier. And if you have conjugate sample, you can use them as either negative, which is basically the second column of positive as the third column, or you can use this the way that I propose, jointly learning an action extractor, contextual extractor, and the classifier. So on average, the proposed approach might have significant improvement over the other approaches. And in some cases, you can observe a large performance gap between the proposed approach and the second best alternative. And in some cases, using conjugate sample as either positive or negative example might hurt the performance of a classifier. For example, if you look at the class Hi-Fi, you can see that if you use a conjugate sample as a negative training example, it will significantly lower the performance of the classifier. So Hi-Fi is an action that occurs very briefly. So the context is very important for recognizing the action. If you use the conjugate sample as a negative example, then you basically ignore the importance of the context, and in this case, it will degrade the performance of the classifier. Okay, so let me show you some video clips that excite the action and context channel the most. So, for example, for answer phones, these are the what I'm showing here is on the left are are the video clips that that has high activation score for answer phone. Okay, and on the right are the ones that with high activation score for the contextual component of answer phone. Here are some other examples for other action classes: hug, handshake, and sit up. For example, if you look at the if you look at this this particular example, basically, which it suggests is these are in this situation, the two people are likely to hug each other. We can also analyze the pairwise contextual differences between different action classes. So what we did is we consider the pairwise contextual differences, and here we consider the get out car classifier, and this figure shows the differences between get out car and other categories. So the smaller the bar, the higher the similarity between the two actions. So what this one shows is basically, drive car is contextually similar to get out car. Okay, because in Hollywood movie, usually if they want to show that someone get out of car, they will first show that the person drives the car before he gets out of the car. Another action that is also contextually similar to get out car is run. So again, in TV material, a lot of the cases, a person get out of the car and they start running. Okay. This is for another classifier, the kiss classifier. In this case, what you say hug is contextually similar to kiss, and this is quite intuitive. Okay. We can also analyze the role of context features. Now, being able to separate action component from the context component gives us some flexibility we can tune the contribution of the context component for classification. For example, if we consider separating between contextually similar pairs, this column basically using both the action and the context component for classification, and this basically not using the context for classification. What to say is for contextually similar pair, if you use the context for in making the decision, then it actually hurts the performance of the classifier. However, for contextually dissimilar pair, context is very important. For example, if you consider between kiss and it, if you want to separate between kiss and it, then if you do not use context, then the performance of the classifier will be lower than if you using context for classification. Okay, we can also visualize the pixels that correspond to the action and the pixels that correspond to the context in the video. For example, this one I'm showing here is the pixel that correspond to the answer phone, and these are the pixel, the activated region for the context map. This is the same thing for kiss, and these are the location responsible for the kiss, and then this here are a few other examples for eat and sit down. On the left are the action map, and on the right are the context map. Okay, so I basically just finished the first part of my talk on a specific project on attentive action context factorization. Basically, the take-home message for this part is important to pay attention to relevant information and don't throw away data and use it to guide the attention mechanism. Any questions so far? Maybe I just yes.
Maybe a very brief question. What classifier was actually used? Was it a neural network, or do you still make use of an SVM-based approach?
So yes, it's a neural network. Yes. We have basically two stages. One is feature extraction, which is based on the C3D network, and then there's a yes.
Just to add to what sort of method did you use to avoid overfitting?
What sort of method we use to avoid overfitting?
Yeah.
What sort of method? Yeah. So in this case, there's several ways to avoid overfitting. In this case, first of all, the network that we started with the backbone network for training the classifier was pre-trained on 10,000 of video clip or like 100,000 of video clips. So this is the backbone network that has been trained on a lot of training examples. And what we do is that basically fine-tune it on our data set. So that helps a lot.
So you use the video as an input,
yes,
but you're only using the image of it. What if we use the voice or sound to improve that case?
Right. So excellent question. Right now, what we I think is very important is what is the visual and audio cue for recognition. But right now, I think the problem in visual recognition is challenging enough that we kind of focus on this first. Yes.
When you're generating the conjugate samples, do you get a lot of false positives?
Do we get a lot of false positives? Yes, we do. Yes. So right. So we do have. I think I could say the ratio between clean or false positive is about 20 to 30%.
Okay.
Yeah. Yes.
So is it possible creating a new scene by putting different actions in the same context?
Yeah, I think it's a good suggestion, but it's also quite difficult to generate like visually good synthetic example of human action. For some certain problem, like for generating images, I think it works pretty well, but for dynamic video and human action, I haven't seen anything that's very good yet. Okay, so maybe let me move on and talk about give you an overview of other research projects that I'm working on. So the first project is on early recognition of human action using multiple cameras. Now, so early event detection is important, and there are many situations where early detection is important and needed here. For example, elderly people have high risk of falling. If you can detect a falling event before the person hit the ground, then maybe we can deploy some technology such as wearable airbag. In this case, early detection save a life. Okay. In some cases, some action might be dangerous for elderly people to perform. For example, can you guess what this person is trying to accomplish?
Try to reach higher deck.
Yes, so basically this person is trying to kind of tiptoe and grab something from the top shelf or something like that. And imagine like your 90-year-old grandmother is trying to do this at home. Then you probably want to warn her or stop her from doing so, or she will hurt her back, right? Or have high risk of falling. So suppose we want to build a smarter home by installing a camera and observing the activity of the person in build a smarter home where we can issue like early warning sign for some dangerous activities. However, human activity like basically spread out across both time and space. So maybe a single camera might not be enough for capturing the temporal extent of this activity. We might want to install multiple cameras around this the apartment. The camera can be connected to a central processing server, but however, if you ever experience with security camera, you know how much data it generates, and so usually the data, the camera might be like high definition, high frame rate, but essentially when it reaches to the server, there's some certain limitation. First of all, the network might have limited bandwidth, so you don't really, so the camera doesn't really have the so the actual frames that you observe from the camera might not be like 30 frames per second, but it might be like 5 frames per second. The second problem is even if there's no bandwidth problem, then the server might still have limited processing power. So essentially you have to drop the frames. Okay. But however, uniformly dropping the frame of each camera might not be the right policy here. So the research question in this course that we study is how do we recognize, suppose this is the event, how do we recognize this event as soon as possible? The limitation of existing event detectors is suppose this is the current moment and this is the part of the videos that you already observed, and this part is that you haven't observed yet. So you have to detect and recognize the event even before the event is complete. And so at this current moment, you have two options. Either you delay making the decision until you see the full event, or you make the decision right here and settle for unreliable decision because our detector wasn't trained to recognize the partial event. The second issue with this is suppose that you have multiple cameras and some camera might give you better information about the action than other cameras. The first camera might be has a frontal view but is blocked by a table. The second camera might see the person from the full scene, but the person is very small from that camera, and the third camera might not see the person at all. So how do we choose which camera to analyze at each time, given that we cannot analyze all the camera at once? So in this work, what we propose is a system of multiple cameras and treat it as an intelligent agent, and view selection and recognition as a sequential decision process, and we formulate this as a partially observable Markov decision process. So basically this diagram here is basically the floor plan of what we call the home of the future lab at SUNY Brook. It's a one-bedroom apartment with bedroom, kitchen, bathroom, and the layout is pretty much like the diagram below. And this is how it looks like. Basically, we have already installed a bunch of cameras around the apartment. In total, we have 18 cameras around the apartment. The hardware is already there. We are looking for students who can work on this project. So this is a project also jointly with Professor Samaras here. If anyone is, Jihoon probably knows this former future lab very much. The second, another project that I'm working on is called action prediction using egocentric camera. So imagine that you want to build a robot that can collaborate with human. For a fluent collaboration between the robot and the human, the robot must recognize the action of the person and also anticipate what the person is trying to do. Otherwise, the collaboration would be very unnatural in kind of lockstep. The robot must wait for the person to finish the action before it can carry on the next action. Okay. So we don't have a lot of data in terms of human-robot collaboration yet. So we are using a kind of a proxy data set to study action anticipation instead. And what we are using right now is the Epic-Kitchen Dataset. So essentially, there's 1,000 video in the kitchen, and the task is try to anticipate what the person is trying to do in the next second or 2 seconds, given what you have observed. So what we propose here is a knowledge distillation method. Basically, if we have a method to recognize the action, how can we use it to guide the attention, the anticipation network to focus on the right information to anticipate, to correctly anticipate what's going to occur. We also create a BusyHand Dataset. This is the dataset where we create both realistic and synthetic images of people working with tools. These are some examples of the dataset. Okay, another project also together with Professor Samaras here is on predicting visual attention. So essentially, what we want to do is given if we want to predict where a person is going to focus their attention on, if we show them an image or video, when they look at the face of the couple here, the face of the dog, or some other object in the scene. Okay. In order for us to predict visual attention, we need to understand how humans view the world. Okay. So this is very simplified. The human eye is a very complicated organ, but it's a simplified diagram of the major component of the human eyes. The major component is probably the lens here. It focuses the light, so this is the scene, and the light is reflected from the scene through the lens, and it will be projected from the retina here. Okay. So basically, what we see is the image in the retina, but in the retina here there's a very small area called the fovea. Unless this part of the scene is basically on this small area, you only see a sharp image of the scene. Otherwise, you only have the blur vision or blur image of the scene. Okay, so if the scene is on the center, then you see, clearly some letter here. This goes to the fovea region where you clearly see, what inside that area. The next region is called the parafovea region, where you only see 24 to 30 blurry letters. And the next area is called the peripheral region, or you only see the gold shape but not the letters. Okay. So in order for human to make sense of the scene, we need to make multiple fixation. Maybe the first fixation is some location of an image. The second fixation on some other location, and we build up a mental map of the scene basically through a multiple fixation. So our objective in this work is try to predict the sequence of fixation, where people are going to fixate on, and the sequence of fixation given an image or a scene here. For this project, we need to collect some gaze behavior data, and the way we do it is to bring subject to our lab. We show them images and video and record their gaze. So the typical task is the visual search. So we would ask the subject to find some target in the image. We show them an image and ask them to find some target, like find the clock, find the microwave, and we record the sequence of fixation. We would collect gaze behavior data for many images from the subject and many images, and so far we have collected COCO-Search18 Dataset, which contain more than 6,000 images of 18 categories, each with at least 100 images, and we have 10 subjects in total. For this work, we're treating it as a Markov decision process. Basically, we want to learn, the viewer is an Asian, and we use reinforcement learning to learn to learn a policy to predict how people are going to how people look at images. Okay. So another course that I'm working on is for hand detection. So the goal of our work is to try to detect hands and hand orientation in images, like what we call in the Y images here. So our network is what we propose is a hand detector. We have the state-of-the-art hand detector, and it's based on mass RCNN with two innovations. One is the similarity context, one is the semantic context. And okay, so let me show you some hand detection result. So comparing with some other state-of-the-art method, mass RCNN, our method doesn't detect the hands. The other state-of-the-art method is confused between, it often have like 4 detection here. It actually detect feet as hands, because locally feet and hand look quite similar. So our detector can resolve this ambiguity using the contextual cue instead of just looking at what inside the proposal region. Let me show you some of the Okay. So so this is frame by frame detection. There's no temporal smoothing. So this work will be presented at ICCB 19, which is occurring right now. Well, the final project that I want to tell you about is crowd counting. So basically, the task is given an image. We want to know how many people in this image. We build a network that can not only count the number of people in the image, but also estimate the density at different locations of the image. So here are some results. Basically, on the left is the input image, the ground truth image in the middle, and the output is what is the output of the network. Here's some other result of, this is the output of our system. Okay, in summary, basically, the first part of the talk, I explained one specific project, attentive action and context factorization, and I also give you a brief overview of other research projects, and that's it. Thank you very much.